you, Higino, for organizing and inviting me. The pleasure to be able to talk to the fast-growing community of data scientists within Brazil and Sao Paulo. It's really cool that you have a new community going on here, and it's great to see actually data science kind of going on beyond the borders of the states and kind of affecting all corners of the world now. So today I'm very excited to talk to you about the differences between data science in academia and data science in industry, and why these differences are actually a barrier for academics or former academics to make that transition into industry, and what you can actually do to overcome these barriers. Higino did a great job of introducing me, so I won't belabor the point there. I split the talk into two different parts. I'll start off with basically the good news and tell you why academics are so well suited for data science. But if that's all you wanted to hear, you wouldn't be listening to this seminar. So the second part, we'll be talking about, basically the majority of the talk will be concentrating on the bad news, which is that there is a cultural barrier between academia and industry. And this is actually centered around two stereotypes of academics. And I'll show you basically how to prove these stereotypes wrong and overcome that barrier. All right, so let's get started. At first blush, it can seem that this transition should be easy. Many of you have probably seen this Venn diagram by Drew Conway, which in a rough sense defines the skills of a data scientist. Broadly, it separates the skills into three areas. The first area being substantive expertise. This is where you really need to understand the background knowledge of the field that you'll be studying. So if it's marketing, you really need to understand marketing. If it's something completely different like insurance or energy policy, that's what you need to study. The second area here is mathematics and statistics knowledge. These are the quantitative skills that you need to accurately extract insight from the data. And finally, the third area is called hacking skills, what Drew Conway calls hacking skills. These are coding or programming skills needed to properly interact with the raw forms of the data and execute your plan of analysis on the data. So when Drew Conway first proposed this diagram, he called the intersection between math and statistics and the substantive expertise area that small area called traditional research. But I think now that things have changed to where a lot of academics actually incorporate all three of these areas in their research. An academic in particle physics, for example, needs to have a deep understanding within the area of particle physics, so that's the domain knowledge. Has to be able to code to work with the data and execute analysis, that's the coding part, the middle, and needs to have knowledge in mathematics and statistics to accurately analyze the data and come to a proper conclusion. So that's the math and stats on the right. And this is actually results from the Higgs boson discovery paper. The same can be true for a biologist. So he or she needs to have a strong understanding of the underlying field of biology, must be able to code to work with the data in complicated ways, and then also have the quantitative skills to draw conclusions on analysis. And so it's no wonder that DJ Patel, who is the chief data scientist of the United States, he also co-coined the phrase data science. He says this: the best data scientists tend to be hard scientists, particularly physicists rather than computer science majors. Physicists have a strong mathematical background, computing skills, and come from a discipline in which survival depends on getting the most from the data. They have to think about the big picture, the big problem. So I would agree with DJ in that best data scientists do tend to come from science, but I would also disagree with him in that I believe that social scientists are just as well equipped these days to match those three areas that I talked about before: the domain knowledge, the math and statistics, and the coding. And in fact, I think basically all quantitative academic fields have some representation here. Physics, all the different types of engineering you can think of, applied math, psychology, architecture, economics. These are all areas that incorporate hacking skills, math and statistics, and substantive expertise. Well, when I graduated with a PhD in applied physics a few years ago, given all this, I thought, oh man, I'm already a data scientist. Getting a job in data science is going to be so easy. I tried this, and man, was I wrong. As I was nearing graduation, I was applying to these data science jobs and just not finding a whole lot of success. Things were much harder than I anticipated. And honestly, everyone told me any career transition like this is going to be hard, but I thought it was going to be a lot easier. It was not. But I'm here to tell you that it's not impossible, and you should never think that this transition is impossible. So I ended up being accepted to this program called the Inside Data Science Fellows Program. We help PhDs transition from data science to industry through a 7-week course program. And I learned a lot working with other PhDs and through the mentorship of other data scientists within industry. I stayed on board, actually, to help other PhDs make this transition and for about 2 years. And during that time, we helped about 300 academics make that transition to industry. And so we worked very close with industry, and during that time, I learned basically that the most important barrier is actually not a technical one. It's a cultural barrier. So sure, you need to learn to fill in the gaps. You need to learn the technical skills to do programming and math. But for the most part, you basically already have those technical skills, especially if you came from a quantitative field like engineering or physics or quantitative biology or psychology even. So what I want to talk about today is to summarize this barrier. And the way I see it is it can be summarized in 2 stereotypes of academics. And you'll have to break those in order to cross over. So those stereotypes are, 1, academics can't understand my business. And then 2, academics take forever to do anything. So let's understand these stereotypes and figure out how to break them. So the first stereotype is that academics can't understand my business. How do you go from operating a machine and studying, let's say, carrier multiplication in quantum well solar cells, like on the left where they grew semiconductor devices layer by layer? Right? How do you go from that to understanding how to make sure my website customers come back, or how to score a loan for a bank? This just seems like too big of a jump. And so, basically, I want to know how a PhD in physics or applied physics or engineering or whatnot can help me improve my business. So it's kind of a jump, and it's not that hard to understand. The best way to fight this stereotype is to do a project that shows that you can understand the business. To do a project that solves a real and relevant problem. If you're interested in healthcare, do a data science project in healthcare. If you're interested in politics, do something in politics. If it's in sports, do a project in sports. Finance, do a project in finance. The list goes on and on. In fact, there's many more example projects out there, and even more than that, there are a lot more potential areas that you could do projects in. And these are just some of those areas. If none of these sound interesting to you, just think of a problem that you yourself have. Can it be answered in a convincing, quantifiable way with data? And I would say when you're going about this, the hardest part of data science is defining the problem. It's not doing the modeling or even cleaning the data, even though I bet some of the data scientists out there would disagree with me on that. The hardest problem is actually defining the problem. So show that you can come up with a compelling project idea, a compelling problem. Many people ask me when they get started, but where can I get the data? I don't know where the data is on that. They always get hung up on the data. So when you start, don't worry about the data. When you start, focus on the problem. If you start focusing on the data, what you're going to do is you'll find yourself solving the most obvious problem that data provides. And that leads to basically uninteresting projects, and you won't be able to show off your creative abilities. The creative abilities that you honed through school, lots of those years in research. Always focus on the problem first, then execute your project. And if you're outside the field, if your project is outside of your typical academic field, you're solving a real problem that affects other people, you're going to start convincing people that, hey, you can actually learn to help me with my business. So to overcome that first stereotype, prove that you can, 1, understand a domain, 2, define a problem, and 3, solve it. So that's the first stereotype, and that's how you get over that hump. The second stereotype is that basically that academics take forever. They're too slow. Oops, excuse me. They're too slow. They're perfectionists who basically take forever to come back with results and recommendations. They focus on the details and end up wasting tons of time. So how could they possibly keep up with my business that moves so fast? So having been in academia, I think there is some truth to this. But actually, having been in academia, I also think it's a good thing. At least for academics. So let me give you an example. This is a very oversimplified history of physics. So just in order to start somewhere, I'm going to start with Newton back in 1627. So that's at the very bottom of your screen, where F equals ma. That's when Newton published his formula and his laws of motion. About 100 years later, building off of that concept of Newtonian physics, we get scientists who are discovering the laws of thermodynamics and mechanics. And then 100 years after that, they build off of those two things and start understanding electrostatics and magnetism. And then about 60 years, 50 to 60 years after that, Maxwell kind of combines all these ideas together in Maxwell's equations. Then physics starts really accelerating. 50 years later, we get relativity and quantum mechanics, ideas that are so foreign that I think we're still struggling to understand, like modern day scientists are still trying to understand what really is happening there. And before we've understood that, we now have the Standard Model, which kind of describes all of the particles within physics. And we're now standing on the edge of physics where the big thing that's supposed to explain everything is string theory, but it's so complex that it's untestable to actually explain, untestable, so we can't actually experiment on it, and who knows where we'll go. But there are a few things I want to point out here. The first thing is that this took a very long time. So this timeline, this very simplified history, is about 400 years. And all of it was basically built on the 3 laws of motion at the very bottom. So if Newton and the rest of the scientific community were not absolutely sure that the laws of motion were correct, or at least approximately correct, the whole thing would collapse. And so we want to be sure that what we're doing is absolutely correct, so we have time. And we can take our time because we are describing truths that are not changing. They don't change. The laws of the universe are basically the same yesterday as they are today. They're probably going to be the same hundreds, thousands, tens of thousands, hundreds of thousands, maybe millions of years into the future. So we can take our time. Also, the third thing is credit goes to the individuals. Work is done by individuals and small groups. This is actually important because there must be unbiased validation. Even in the search for the Higgs boson, that was the largest scientific collaboration in history. There were 2 groups searching at the same time to make sure they were independent, unbiased verification of experiments. And so in the late, about 10 years ago, we had the discovery of the Higgs boson. Or no, it was less than 10 years ago. But essentially, there is a trade-off, and that trade-off is between certainty and speed. So when you have absolute certainty, or when you need to have absolute certainty, or about 99.999% certainty, this can take a really long time, and that's where we are in academia. That describes academia in the lower right. And this works because you're basically looking for unchanging truths. Knowledge builds exponentially, so you want to make sure that the foundations are solid. On the other side of this, in the top left corner, is when your truths continuously change. So this is often the case in adversarial industries. So the knowledge, what that means again is that the knowledge that you discovered yesterday was true yesterday, but today maybe it's not true. So industries like information security or financial traders, these are people who are faced in this world every day. They must work really, really quickly to discover new knowledge, and that new knowledge, they must use that new knowledge before it becomes stale and useless. And they have to go really quickly. But if they don't go quickly enough, they're in trouble. The payoff there is, or the trade-off there is that if they go really, really quickly, they're often not going to be 100 or 99.999% that things are absolutely certain. The things that they're discovering are certain. So maybe they're 90% sure, maybe they're 80% sure. So that's a trade-off. Most corporate data science teams operate in this orange region. Unlike academia, you don't have to, where you have years to come up with new knowledge. You have a shorter amount of time. But you get to maybe 80% of the way there, and then you see if it's good enough to act upon. In other words, data science and industry works much, much faster than academia. So to make that transition, you're going to need to learn how to go fast and learn fast. And you need to prove that you can do this. But just because I said that doesn't mean now that you have some superpowers to make you go 10 times faster. So how do you do this? Well, you can do this because you're not constrained to work alone anymore. You don't have to worry about getting scooped on some papers or anything like that. You can just execute and learn in groups. And so why would you want to do that? Well, the research has shown that the fastest way to learn is through your peers in a group setting. And this has been borne out by lots of educational research. And you can learn also organizational best practices as a result. So data science and industry is done in groups, so you should learn how to work in groups if you want to make that transition. And this is also the same things that we taught in Insight, where group learning is highly encouraged. So at Domino, we build an enterprise data science platform, and we work with large data science organizations. And these organizations must work in groups to keep moving fast and building knowledge exponentially. But it always brings some challenges. So the first challenge is knowledge management. Basically, it's hard to know what your organization knows. And too often I hear people saying, man, I just constantly find myself reinventing the wheel. So Google solved this problem for the internet. Data science is actually a little bit harder to solve this because you need the context. So when you're working together, you'll need to plan out how to manage the knowledge that your group produces. Where is the code that cleans the data? Where is the code that visualizes data? Do I keep those separate or together with the data? And the bigger your group, the better the system that you'll have to use will be. The second thing is reproducibility. This kind of comes from the previous point. Once I have found the work that I need, a lot of times you'll find that just copying and pasting the code doesn't work. You'll find different results, or even worse, the code just won't work, and you'll find an error. Often, the environment of the code the environment that you actually execute the code in will really matter. The data that you operated on really matters as well. So you can imagine where the data changes, but the code doesn't change, you're going to get a different result. The version of the package changes, but the code doesn't change, you're going to get a different result. So as you work together, keep in mind that you will need to keep track of the environment, the exact versions of the packages that you use, and the context in which you executed the code. So remember that as you're trying to collaborate. The third point is collaboration. So you want to be able to look and share the code, make it better as a group. And as you're learning as a group, you probably are not going to all know the same thing. Some of you may know Bayesian statistics really well. Others of you are really good at visualization, and others of you just are really good at algorithms. The best result happens when all of you, the best people, contribute to the work, and where you can spread that knowledge and spread your skills. And basically, you're learning from each other. So finding a good way to collaborate is absolutely essential, whether it's emailing files, using Dropbox, what have you. And finally, after working on a project, you're going to need to share those results. If you want to, you basically really want to show off all of your hard work. Usually there are basically three groups of people that you want to share your projects with. The first group is your collaborators. We just talked about that. The second group is non-technical people. These are people like your executives, CEOs, or people basically who just don't want to look at code, but are still interested in your results. You might want to share PDF, a file, or maybe a web page. The third group of people are technical people, but they speak a different language. So if you're programming in Python and your engineering team is working in Ruby, there is going to be some translation there that's needed. So oftentimes, data science teams use an API to efficiently communicate. Regardless of who you're sharing your results with, it's really important to think about how you want to do that, make it appropriate for the audience. So these are some common group challenges that we see. But despite these challenges of working in groups, a large, sophisticated team all find that working together in groups is still the fastest way to learn and work. So I hope these challenges won't stop you from working in groups together. In fact, I hope that these list of challenges will actually help you work in groups even better now that you know these challenges. So just to summarize here, the second stereotype, that academics take forever to do everything, prove that you can learn and execute quickly by working together, and that will help you overcome the stereotype. So to summarize the entire talk, I just wanted to say again, the biggest barrier between academia and industry is cultural, and you'll find you're basically fighting two different stereotypes. The first stereotype being academics can't understand my business, so to overcome that, do a project that actually solves a real problem. Show your versatility. The second stereotype is that academics take forever to do everything. So prove them wrong. Do work quickly by working together. And so you'll find after that you'll celebrate, you'll make the transition, and you'll be good. So I'm happy to take any questions. And just if you have any other questions and we don't get time to them, you can send me an email at my email here at johnju@dominodataLab.com. Thanks.
Could you share a little bit about this transition? Because I guess a few people here in Brazil, of course, facing the same challenge with a good expertise in academia, leaving some areas, masters, etc., and think about the corporative world.
Yeah, absolutely. So when I was academic, I knew that I didn't want to continue my career in academia. The faculty, the postdoc, the whole world seemed a little bit, which is just not for me, actually. So when I was in school, I looked at other options. Those other options usually found me in two different fields, consulting or finance. And I knew that I didn't want to go into either one of those, but I still liked aspects of both of them. I liked the fact that you were doing real-world problems and you are affecting real change in consulting. In finance, I love the fact that you were really working with quantitative elements, that there was a right and a wrong answer. And so it felt much more like research to me. So that's when I heard about data science, and I was like really excited to work in data science. What I found was that as I was trying to make this transition, you know, like I've been working for several years on my PhD. I knew, like, I was taking courses on machine learning. I was very familiar with the math and the quantitative side of things. But there were certain things that I didn't know. For example, like SQL, like the fact that all of industry basically operates on SQL. And you know, as a physicist, I was very used to putting everything in flat files, like CSV files. And you know, industry does that too. But if you don't know SQL, it's going to be impossible to get your data. So that's just one aspect of it. But then there were other things, like small things in both math and statistics, as well as computing, that I didn't have a formal knowledge of, and so Insight gave me a great opportunity to fill in those pieces by actually doing a real project. And as I did my project, I found that those holes were revealed, and I can easily, quickly go and fill those holes. And I was doing it fast and I was motivated because there was a real purpose behind it. I was trying to make a project that affected real change.
Okay, thank you. Paulo Abreu is asking, what if the company does not have a sharing culture?
Yeah, I think there are two ways to think about a sharing culture. The first way is thinking, oh, okay, does this company support open source code? Okay, so that's one aspect of a sharing culture. If they don't, that doesn't necessarily mean that within the company that they don't share with each other. So you can imagine a company like a financial company, for example. They are probably guarding their secrets very highly. So they don't want to share, you know, all their investment ideas with the outside world. That's how they make money. And so from the outside, it might look like they don't share. But from the inside, my guess is that they would share with each other, at least, the things that they have learned, because that's how you build knowledge. If you're not, you know, if you are currently working in a company with a culture that, you know, they really don't share information, they don't share code, I would suggest that that's sort of like a backwards area. Like you really want to be at a company where you can learn, where data is like a very core part of what they do, and research is a really core part of what they do. And so to have that, you're just going to need to have that kind of a sharing culture.
Raphael Smith is asking, do you use any methodology framework to manage these projects, like proposed by CAPS, Certified Analytics Professional, for example?
Yeah, absolutely. So that's actually what Domino Data Lab does. Let me see if I can go back. So if you want to find out more about what Domino Data Lab does, you can just go to our website, www.dominodatalab.com. A lot of these challenges, a lot of the reason that these customers buy Domino is because we do a really good job of making sure that these problems are solved. And the software kind of helps you do that. There are a lot of different data science best practices that help you solve these problems. So, for example, knowledge management. You want to have some kind of organization, so to tag your results somehow, or to provide good descriptions of your project so that you can search these things later on. Reproducibility, you want to really keep track of everything, basically everything, like all of your files that you want to, that depend on the code that you're executing, and you also want to keep track of all the results that happen. So this can be laborsome, so that's why Domino does it for a lot of our customers. Collaboration, again, this is sort of something that occurs if you have all of your work in one place. So I know a lot of companies, engineering companies, for them, GitHub is the place where everything works in one place. For a lot of sales organizations, Salesforce or their CRM is the place that they store all of that information. And so collaboration becomes really easy. At Domino, we think that Domino could be a place where all that work can be stored. That makes collaboration really easy. And then the sharing results, once you have that collaboration, you make the sharing results super easy as well.
Okay, thank you. Fabio Aquino is asking, how about those companies that aren't data-driven just yet? Any tips on how to approach them?
Yeah, I think this is kind of true for any company that you're going to go to. You should find out as much as you can about the company. So, let's take one of the customers here. Let's say I was working if I wanted a job at Tesla, and assuming in this very weird world that Tesla was not a data-driven company. If I wanted to work at Tesla, I would go in and just learn everything about Tesla. Go do a Google search on Tesla. I would go to their website, click on every single button that I saw, just understand their product from inside out. Okay, and then I would say, figure out how I could provide value to them. So if I'm a data scientist, that's why I said defining the problem is the most important thing. Defining a project. So how would you be able to make money for them given your data science abilities? And show them your value that you can bring if they became a data-driven organization.
Okay. Gabriel, thanks. Gabriel Santucci is asking, to move to industry, is it essential to enter a program like inside data science or that incubator?
No, absolutely not. I would say that it becomes a lot faster if you do that, but absolutely not. I think a lot of people can make this transition on their own. There's definitely proof of a lot of academics making this transition on their own. I think the key ingredients are that you want to basically be very close to industry. So if you're in Brazil, you guys are doing exactly what I would recommend. Go to meetups, take in as much as possible what data science looks like in industry. Learn their language, learn what they do. And then I would form groups and study the things that make me a good data scientist, kind of going back to this diagram, hacking skills, learn the computer science essentials, the fundamentals like sorting algorithms, different data structures, math and statistics, learn machine learning, learn statistical learning. I guess those are basically the same thing, but learn statistics. Math and statistics are not the same thing, so understand those. And then in the expertise, again, this is sort of what you're doing right now by going to meetups and learning as much as you can from data science. If you do these things and you do them in groups, basically you're going to get a lot of what you need to make this transition.
Mm-hmm. Fantastic. Silvana Shavena, for basic scientists like me, it's more difficult to know what is a real problem in an industry that we can help to solve. So my question is, why the industries do not approach the academics with the project draft? Thanks, Silvana.
Yeah, that's a really good question. So I do think that more and more industry is approaching academics, but I think the reason that they don't is because of these two things, right? I think the industry is becoming more convinced that academia can help with their business. However, I don't think that they're becoming convinced that academics can do things quickly. So for a lot of these different data science organizations, the problem that they need to solve has a deadline. And it's on the order that is much shorter than a PhD student's PhD. It's less than 5 years. It's less than 4 years. It's often like a month. So I don't think I think that's part of the reason that they don't approach academia. But for very big problems that do fit academia very well, I do think there is some approaching there. And you find competitions like Kaggle where international corporations provide challenges to where anyone can contribute to that to their knowledge base.
What would be your, let's say, minimum suggestion to build up your own tech stack as a data scientist if you are not able to attend a boot camp like inside New York Academy or Galvanize that for Brazilian, let's say, salary, very, very expensive?
Absolutely. That's a great question. I get this question all the time. So let me first point you to a resource. The InsideDataScience.com blog has a great resource on getting into data science and basically building out your tech stack there. There are 5 things that are really important for a data scientist. 5 skills. The first thing is communication, and this is probably the thing that is least emphasized, but is actually the most important thing about becoming a data scientist. Oftentimes you're working with people who are not that quantitative, so it's really important for you to be able to communicate your results and communicate your value. The second thing is the technical part, the computer science fundamentals. And so that's irrelevant of the exact language that you choose. I would suggest, though, that you start off with Python. And the reason that I would suggest this is it's a very simple and expressive language. It's not as ugly. It's not as detail-oriented as Java and C, for example. But it's also a fully formed programming language made by computer scientists. Made by not data scientists. So engineers would understand this as well, which is a little bit unlike R, which is R is by statisticians, made for statisticians. So that's why I would suggest Python to start.
Mm-hmm.
Statistics is something that the third pillar, I guess, statistics, and machine learning, fourth pillar. And then finally, SQL. So actually, I should have probably made SQL right after computer science. SQL is probably one of the most important things that you can learn. The flavor of SQL doesn't really matter, but you should learn SQL. So I would say communication, computer science fundamentals, and then SQL. And then those 2, like statistics and machine learning, come later. And I think that probably most of you are pretty good at those already, so that's why I put them down lower on the list.
Okay, just related with Domino, of course, a big decision for some, let's say, company that's a middle-sized company from finance or from insurance, etc., telco, would be the decision to build up from scratch this data science team, or of course, go to a different path of hire one person and using a platform like Domino. How a company that is in need to establish and to look to produce, speed up data science, what be the best way to go, or second, how this company could, let's say, profit from Domino platform?
Sure, that's a great question. So let me preface that answer by saying that Domino isn't meant to replace any data scientist. There's no substitute for having really good data scientists. So if you're really building a data science team in industry, your number one priority should be to find good data scientists. And I think it is a great place to find them. What you need to do is really evaluate not necessarily on the skills right now, but skills, how fast they can learn skills. So I would say data challenges are a great way to find that. So give the academic a data set and say, hey, what can you learn from this data set? Or give them a problem and say, I need to increase my the number of customers returning to my site. Here are the A/B test results. What can you tell me? And so this really shows you, hey, how fast can they learn, even though they don't have the background. And you really want to invest in someone who can learn really quickly. So that's the first part of the question. The second part of the question, I think, is how do I make this decision on whether or not to build this data science platform like Domino or to buy it from Domino? And I think that the answer is sort of complex. I think that there are a lot of things out there right now that are used by lots of teams, like Git, like GitHub, Salesforce.com, things like this. And for the most part, people don't buy these. People don't create these things all again. It's actually a really complicated enterprise to try to recreate everything. And so it's actually much cheaper and much more efficient if you were to buy some kind of data science platform. And obviously I have my bias in thinking that Domino is best. So that's how I would think about it. And then once you have that, you can accelerate the production of your data science team to be much faster. You can reap the benefits of your data science team much quicker once you do have a data science platform.
I think the last question from Silvana, the speed necessary for industries make money is negatively correlated with quality. I think for academia, quality is absolutely necessary. That's the reason for the take forever to do idea. But here's the question: how to deal with the quality and the rush in difficult tasks? Is a broad question.
Yeah, that's a really good question. So if you go back, let me go back to this graph. This is the downward negative correlation that you were talking about, Savannah. So I totally agree. There is this negative correlation. How do you go at the speed as this like changing industry, changing truth, this adversarial, the top left corner, but still gain certainty and knowledge? I think that the answer is like, it's really, really hard. If you are in a adversarial industry and you're trying to push right and not follow this trend, it's actually very hard. You just have to get better. And that's not the answer that you want. What you do in industry is, in academia, you kind of come up with a problem, and then you keep going until it's solved. In industry, what happens is you go for a short amount of time, even if it's a very complex thing. And you go for a short amount of time and you say, okay, I am going to make a milestone for myself and then reevaluate what I'm doing after that short amount of time and see how far I've gotten. And if I've gotten a far a ways and it's good enough, then that's good enough. I stop. If it's not good enough, but it's still really, really important, then I can keep going and kind of adjust my directions based on the suggestions from my colleagues, based on the evolving facts of the industry. And then if I can also abandon it. If things change and I don't need that anymore. Let's say I was trying to find why this peak on this graph existed, and so I'm doing some very deep, complicated neural network algorithm to try to find this, and then the next day it's gone, and I don't need to worry about it anymore. So I just cancel it and I move on to a different task.